we at? 442. 442? 442. This is page 442. So what we're assuming is because there's a little bit more weight in the back of the boat with the motor and the person back there, that the boat's going to rock back a little bit into the water, similar to this dam here kind of rocking around that front point. So we're going to assume that the water reaction on the boat's going to be a little bit stronger back there, okay? And we'll assume it's a linear relationship. And so what we want to do is find the reaction of the water on the boat. And we're going to assume that it's a load diagram as shown. It's a trapezoidal load diagram. So let's get this figured up here. Now, what we're going to do, we've got this trapezoidal load diagram. We've got the two weights of the motor and person back there, and then we've got the boat itself. And then what we're going to do here is assume this is a trapezoidal load diagram. So what we'll do with that is we'll cut that into a triangle and a rectangle, as we do with these. So we'll run that line straight across and get a little right triangle there with a rectangle. So why don't you get the centroids of the triangle and the rectangle? Okay, so we got those dimensions in there from A. We got a total length of the thing of 2.4 meters, right? Okay. So what we're doing here, we're finding the centroids of the loading diagram, and we've broken it up into two pieces, a rectangle and a triangle. So there'll be upward forces directed through the centroids. There are the loads. So if we go half of 2.4, and that ought to be 1.2, eh? And then 2/3 of 2.4, because we're coming from the vertex, right? Otherwise known as 1.6. There we go. Okay. All right, so this problem's a little different in that the distributed load is the unknown on this one, you know, which just makes it a little bit more complicated, but we can work through it. We just do the regular old statics thing, but we just have to approach it just slightly differently. So what we'll do here is we'll call the left-hand side P1, and P is used for loading sometimes. I don't know. You could use any letter in there you want. It really doesn't matter, but I call it P for load. And then we've got P2 on the right, okay? So we got left and right. And then based on those numbers, we can come up with the areas of the rectangle and the triangle, okay? So that'll be the strategy on that. All right, so the reaction for the rectangle, the height of it is P1, because what I've done here, just to kind of blow it up a little bit, I've taken that diagram that's shaped like this, and I'm calling this P1, and I'm calling the total of this P2. So what do I got? I got P1 right here, and this will be P2 minus P1, right? You all good with that? Okay. And so I'll have 1/2, let's see, for the rectangle then, that area is 2.4, which is the length of the boat, times P1. And then for the triangle, it's 1/2. The base of 2.4 and the height would be P2 minus P1. Okay. And then what I'm going to do, you know, as I often do, I'm going to take moments. So I'm going to start with a moment equation about point A, which isn't on your sketch there, I don't think anyway. So you might, maybe I did put it on there, I don't know. Yeah, so A, I didn't really mark it on your sketch. You might want to throw a point A in there. And then I'll take moments about point A there. See, and what I'm going to have then are these two loads. And this first one is easy enough. It's just 2.4 P1. And then this other one's a little bit more complicated, not too bad, but it's 1.2 P2 minus 1.2 P1. And then I've got the distances that these things are, okay, from the left-hand side. So that's 1.2, and this other is 1.6, okay? So that's what I'm working with. And see, I've only got two unknowns, P1 and 2, but I don't really have an x component of an x equation I can write for this thing. There's nothing at all going on in the x direction. So that leaves me two equations to solve for the two unknowns. And so the two equations are going to be sum of Fy is 0 and sum of Ma is 0. Okay. So that's how I would approach this. So do we got any questions on what we're up to here? We've also got that 900 over here and then 2400 right there. Okay. So then we just write up our equilibrium equations. Sum of Fy is 0 and sum of Ma is 0. And there's a good bit of algebraic manipulation on this, but you know, other than that, that's really about all we're doing. Okay. So the difference on this is that the unknown is the distributed load. That's the difference on this one. Okay. So that's what we get to on that. And then we just go sum of Fy is 0, sum of Ma is 0 after that. All right, so sum of Fy, what are we going to get? We're going to get minus 2400 newtons, minus 900 newtons. Those are the downward forces. And then we just put the two reactions together, the 2.4 P1 and the 1.2 P2 minus 1.2 P1. And then you can sum moments about A also, which will involve all those forces up there that you see times their respective moment arms. Okay. And what I'm doing there, I'm going to have two equations and two unknowns, so I'm just setting up for that. I solve the sum of Fy equation for P1. And then I'll be able to substitute that into the moment equation is the plan there. Okay. So you all okay with that? Okay. And then we want a moment equation. You know, it's got 4 terms in it, so I'll probably look at that diagram. I've got all the dimensions on it that I need, and I've got the forces, so, you know, easy enough. I'll just use the force equation there, and I'll just add moment arms to all those terms. Watch out with the signs is the thing, though, because, you know, the force signs don't relate directly to the moment signs, so put your own signs in there. Okay, counterclockwise plus and clockwise minus. So we'll have the 2400 times the 1.2. And then we'll have the 900 times 2.4. Those are both minus because they're coming around clockwise is what they're going to do about A. Of course, you always have to reference these to the given point that you're working with. And then we've got the reactions. And those are placed at the centroid of the distributed load. So even though the values on the ends of that distributed load are unknown, you do know the locations of the centroid because it's just a rectangle and a triangle. So we've got the rectangular load. That's that one. That's got a moment arm of 1.2. And then you've got the triangular load, which is the last one there. It's that one times 1.6. And both of those are coming back counterclockwise. Of course, they're resisting the weights. So they're positive moment because they're counterclockwise. You don't really want to close, do you? There we go. There we go. Okay. So then you can go ahead and solve for P1. And I did all the algebra underneath because it's a little onerous writing all that stuff down. So I just collected terms, set everything equal to 0, ran through and solved for P1 and 2 there. 5250 is P1 plus 2P2. And then I've got the expression there for P1. Let's see, I worked down through that. It's 5250 minus 2P2, but P1 is also from the equation above, 2750 minus P2. So I substitute that in for P1 and then work through, and I can get P2, and then I can substitute back in and get P1. Okay, so just some algebra there to get through the two equations, two unknowns. Doing okay with that? Yeah. Okay, so that's how you can handle it if you've got a distributed load as an unknown. Okay. Any questions there? Okay. And I did one project, a little bit of a spillway there, and what you do is you figure out the pressure on the soil caused by the dam, the general assumption there is the dam's rotating about its front edge. So you're going to look for the maximum soil pressure that's required to push back. And then hopefully you've got some information on the soils under the dam. And then you relate the strength of the soil under the dam and be sure that it can handle that pressure you're going to put on it by when you apply this force here and try and rotate it like so. So what they do, they get out there and they drill holes, you know, and they pull the soil up and do some testing on it to try and determine its strength, which is probably about the biggest unknown I know in engineering is soil strength. I mean, they write it up, but they always give you a nice report that says how strong it is and all that, but then they always qualify it. Well, we don't really know. It might be this, it might be that, because, you know, soil is pretty weird stuff. I mean, you can drill here, get one thing, drill 10 feet over and get something else and all that.
So that's what safety factors are for.
Yeah, they're big safety factors on soil. A little different thing with soils, but I remember talking to a well driller once, and he said, I don't drill wells, I drill holes. I'll drill a hole anywhere you tell me to. So that's if you ever buy a rural house, you know, a new or build one, maybe, you know, a better way to put it, you'll sweat that when they start drilling that well, because they charge by the foot. And, you know, especially for up on a hill, you usually don't know if you're going to hit water or where and how deep they're going to have to go. So, okay, so we good on that one? Okay. Well, let's have a look at some 3D then. That's always fun. Let's do that. So, you know, if you're doing 3D now, you've got 6 equations. So 6 equations with 6 unknowns. You got 3 force equations and 3 moment equations. So let's see how we can handle that. So let's see. Let's start with a little. All right. So we're on page 450. So page 450. We're just looking at a picture of that. So something like that is what we're looking at. A little vehicle like so. Okay. So let's look at a couple different approaches to designing this. So let's find the reactions at the wheels. Mass of 600 kilograms, center of gravity, I give you the coordinate of that. All reactions are in the z direction, okay? So everything's pushing up or is pushing up basically. So we've got a weight and then we've got the 1 force per wheel. Okay, pushing up on the wheels, and then the weight would be applied at the center of gravity. So remember to get that mass turned into a weight, and then we've got RA, RB, and RC pushing up on each of the wheels. And then we need an approach that we can take to solve this thing, okay? And there's 2 distinct approaches. And on this one, I think I did put 2 handouts in there for you, one on this page and one on the next, if I remember right. So yeah, okay. So let's start with the more intuitive approach, but it does require a bit of visualization abilities here. So, so what we've got there, we got the weight, not the mass, but the weight at the center of gravity, and then upward forces at each of the wheels.
Okay, where is it? Oh, never mind.
Yeah, I just gave you the coordinate on the center of gravity because it's a little messy there. I'm drawing that in there. Okay. All right. Now, the first approach that works, you know, if you can see them, is kind of the quick way to solve some of these. Now, you can't do this with all the 3D problems. Some of them are too complex. But on this type, what I would try and do is turn it into a 2D problem. All right, and the way you turn it into a 2D problem is you visualize it from different directions and do it in such a way that it'll be to your advantage, that will help you to solve for what you want to solve for. So if I were to do this, the first view I would probably have would be this way. So if there's a little I would look right down the y-axis. Okay. There. Okay. So looking down the y-axis, what am I going to see? Why don't you draw up a little sketch of what you would see if you were looking down the y-axis? So what you're doing there, you're looking at the car from the side, right? You'll get into something like that. Okay. Okay, so if you can visualize this stuff, you can come up with, you know, some pretty quick solutions, I think. So on this, what do we got? Now, what I've done here, the R, B, and C are both right in line with each other, aren't they? So I just showed them as one-sided arrows so I could show that there were two of them. There's no other significance to the fact those are one-sided arrows. It just means I'm trying to put them right next to each other. That's all. And then we've got a weight of 5886. So that's the free body diagram looking down the y-axis. So what, how could I solve for RA? So that's a good start. What's the quick way to do it? One equation, get the answer for RA. Good idea, though. I mean, that's kind of the idea. We just want to modify that a little bit. If we just want RA, how would you do it? Moments about? BC. Yeah, BC, or you might call it moments about the y-axis, you know, whatever you want to call it. If you do that, you can solve for RA directly. See, any of these 2D problems you look at in your book are really 3D problems. They're just making them into 2D problems, so you can solve them, right? And those sketches that you get in the book. So you could do that too. I mean, you could take that car and turn it into a 2D problem if you like, okay? So easy enough, eh? So then it just becomes a pretty straight up 2D problem, see? So you just take moments about the y-axis, set it equal to 0. If you're looking down the axis there, the 5886 causes a counterclockwise moment, so that's positive. And then that's 0.9 meters from the y-axis there, the center of gravity. And then you got RA. You can solve for RA. It's 2207 newtons. Okay. You okay with that? Okay, so you just
The
take,
reason why we
yeah.
can turn it into a 2D thing is because we know that the wheels are going, or the back wheels are going to do the same thing and cancel out their moments in the X direction, right?
Well, no, I don't think that the reaction on the two back wheels are equal because the motor isn't, the weight isn't centered on the thing perfectly. So the weight is a little bit offset if you look at where that center of gravity is. So those two back wheels aren't, they don't have equal reactions, if that's what you're saying. I mean, it's hard to understand exactly what you mean, but if the two back wheels are on the y-axis, so that's why you can take one spot the y-axis, because of their location more than the weight, more than the reactions.
Yeah.
Is that, okay. Okay. All right. Now, we good with that? Okay. All right. Now, what's another 2D equation you could throw at this to find another one? What could you do?
You can look at it head on.
Head on, looking down which axis then? Yeah, x-axis. So why don't you all take a moment about the x-axis. Let's take a couple minutes on that, see what you come up with. So draw a picture from the front, like a picture there on the car. Think of what the front of the car looks like. So just draw the picture. So if you're on the y, that'd be this pushing down, and that comes back from the y-axis.
Like if you're looking at it like that, this has a dimension that's up. So you have to be looking at it from the y. Because
Looking when you say it, are we, which one are we going to do?
I was just talking about
The last one, okay. Actually, I think of that more in the XC plane itself. Look at it from this side.
so like when you look at it based on
From the front, this way, down the x-axis. So this would be the YZ plane, but then this one, I think you're referring to the one we did previously. This one is the YZ plane. Well, no, for the previous one, it was the XC, I thought that's what you're saying. So now we're going to look at the YZ. Look at that in front of the car. Yeah, we're just looking right now on the x-axis is what we're doing. All right on that? You'll look down towards the front of the car. Put the wheels in there. What shape are the wheels going to be from that angle?
Rectangular?
Yeah, they're rectangular, yeah. There are going to be 3 of them, eh? So draw that picture, then figure out what equation you could throw at it to get the reactions on the wheels, okay? Okay. Okay, so we're looking down at the front of it. Okay. So there are the three wheels. X-axis is on the wheel to the left. RC is the unknown. We already found that 2207 on the middle front wheel. There's the driver. That's the steering wheel. Kind of more from the impressionistic school of portrait. Where I come from. Okay. And then just take moments about RB, see. Okay, so we're looking at the front of the car. We're using those dimensions. 0.9 is the distance from B to the middle wheel. Center of gravity's offset over there to the right. So that's that was given as a coordinate, so that's 1.1. And then 1.8 to the wheel C. So notice I'm doing that same sort of stuff I did before. I got everything dimensioned from B because I know I'm taking moments about B. So 2207 times 0.9 counterclockwise is positive. And then 1.1 times 5886, that's clockwise, so it's negative. And then the last one here is the unknown, that's RC. That's positive because it's counterclockwise. Okay. Any questions on that? Everybody okay with that stuff there, what we're doing? So we're just doing a little visualization here and getting the, turning the 3D problem into a 2D problem. Just look down a given axis. Or if you want a line parallel to an axis, it doesn't have to be right along the axis. You can look at whatever line suits you. Okay.
So it always be when you make a 3D problem, the line of axis that you're looking down, that'll be the moment you take it about.
Yeah, right, because that's the definition of a 3D moment is the axis of a 3D moment vector, I guess you'd say. It's the axis that you're rotating about. So right, if you look down the x-axis, it's the next moment, right? Yeah. Okay. So that'll get you, so now we got RA and RC. How do you get RB? Yeah, there you go. Yeah, don't be messing with any more moments. Just do a, well, you could. I mean, you could take a moment about C, right, using this picture if you wanted, but yeah, I just do a sum of forces, quicker and easier. You could use this sketch and do a moment about C if you wanted, but it's just extra work and more chance for error. So the last thing I do is be to go sum of Fy. Set that equal to 0, and you can solve for RB. Okay. So RB's unknown, you got the other two reactions, and you got the downward force. And everything equals 0, so you can solve for RB. Okay. That's about it. 2494. No, that's a 4. I didn't do too good with that. There we go. Now that's one way to do those. And what that requires is a bit of ability to visualize, you know. And I mentioned this before, I'd encourage you to develop that ability, you know, it's a good work skill. You know, my own field is civil, you know, if I'm gonna work with a piece of ground, I gotta have an idea what the heck that thing's gonna look like when I'm done, okay? And I have to have that in my mind. If you just got to do more than, you know, push buttons on a calculator to figure stuff out, you know. You want to have that ability to see for certain fields of engineering, okay. If you've taken the drafting class, you probably had those problems where they give you an isometric and they give you some of the lines, but not all of them. You got to kind of figure out what's going where. That's a good exercise to help develop that skill. I've also built little models in my office sometimes just so I had some idea what the heck was going on. I had to endure some people laughing at me, but what the heck, man, help me see it. So whatever I gotta do, I do, you know. You know, nowadays they got 3D modeling programs, and most everything's 3D too, so that's very helpful. You know, heck, by the time you guys are a little ways into your career, there's gonna be no blueprints left. It's all just gonna be 3D models and tablets is basically what it's gonna be. I mean, okay, so there's some of FY. Oh, it just jumped. There we go. Okay. All right, now there's another way to do these if you like, and you can do them with 3D vectors also. I mean, you could do, you know, it's fine to do it that way too. So whatever way suits you, I would encourage you to use. All right. Good. So if we do a vector approach, and I think you got a second page to put this on, it's the next page. Okay. So what you're going to do is just throw a vector equation at this. So it's the same problem. It's just, like I say, a different approach. So we get the weight in newtons, 5886. And then what we would do is take a moment about some point, remembering that moments are r crossed with f. Okay, so I could take a moment about a for this thing. Okay, so what I would do is I would, you know, put my cross products together. And remember, I'm crossing r with f. So I'm going to put in a vector for how I get from a to each of the points. So to get to RA, I go 2.4 in the x direction, that's dimensioned over there. And then I go over 0.9 in the y. So of course all the dimensions are in terms of x and y, so that'll work right out. And then I get IJK, 2.4.90, and 00RA. Now it's 00RA because RA is in the y direction, or excuse me, the z direction. Z is up and down. And then I can do the same thing for RC. Starting at A, you just go 1.8 in the y direction to get there from A. And then it's 00RC that you cross with it. And then you do the weight as well, which is at the center of gravity. Now you can notice that I think you've got dimensions for the center of gravity, but I gave you the coordinate too, so that'll be that last cross product. Now I'm just putting these in a determinate form again, because that's how I learned to do them. You wouldn't have to do them this way, just do the crosses, R crossed with F, but you know, however you do it, I would do that. You know, whatever way you're comfortable with. So here, what do we got? We got I, we got J, we got K, and then you're given the position vector from A to that center of gravity, so 0.9, 1.1, 0.6, and then we've got, what, 0, 0, minus 5886, is that right? something like that. And what that does is it, through this cross product process, is it puts together all the moments for you. Okay? So now, the advantage of this is it's somewhat automated. You know, you just kind of plug in the numbers and you find the position vectors and find the forces, run the crosses. The disadvantage is that, you know, you got to run a lot of crosses, so you got a lot of computations to do, all right? So that's the problem with their, you know, disadvantage or whatever you want to call it. So I just list everything below there. Notice those k vectors all zero out. There's no k moments here. And also notice that these terms I'm coming up with, the I and j terms, they're just the same moments that that we got when we went ahead and did these visually. All a cross product does is automate what you would do visually. It just does it for you. A lot of stuff zeroes out on this, which is good. So I got the I's in the first column there, they're green, and then the J's in the middle column, they're red, and then the K's are all purple, but they're all going to cancel out anyway. And it's the same sort of thing. You'll just sum up the I's and sum up the J's. I think you probably start with the J's and solve for RA, and then plug that into the I equation and solve for RC would be the deal with this one, okay? So this is doing the exact same thing we did manually. It's just kicking it out is all it's doing. Okay. All right, so you get yourself a big old cross product built up there, and then you just collect terms. And again, you're gonna, I do this one a little differently. You know, in the past I've done them where the vectors, well, I don't know, this is a moment equation, so I guess I haven't really done this directly, but now you're gonna solve out columns. You know, before I had you get the I's in a row and the J's in a row and the K's in a row. This one will just solve out the columns, okay? So the equations are in the columns on this one. So the y, I just collected terms there down below on the top line there, and then solve out the y equation. And as I said, it's the same thing as we did manually in a minute ago. It's just done for you automatically with cross products. Yeah.
Do you have your displacement vector right for the wave? Because that looked like it rolls into displacement vector from an A. And
well, it's from A, it's 0.9, 1.1, 0.6. You know, that's, and I know that isn't the prettiest sketch there, that's why I put that vector in there, but you're going up.
I think it should be 1.5, not 1.1.
Is it?
It's 2.4 minus 0.9.
Minus 0.9? Oh, I see. What? No, it's not 2.4. It's just further over than the 0.9. It's not like you're doing 2.4 minus 0.9 there, I don't think. I mean, the 0.9's in the x direction anyways, I think. And we're coming from the origin to that point, to the center of gravity, G, so that's 0.9, I think, as I'm seeing it anyway, but okay, we could go over maybe tomorrow. We're starting to run out of time here, but.
I can't do anything tomorrow.
Oh, well, we could, but yeah, that wouldn't serve any purpose, so maybe Monday. Okay, so we're getting those equations worked out, and then to get the last one, we sum forces in the Z is what we do. And it sounds like you guys don't have anything to do tomorrow, which I will fix that for you, don't worry about it. I'm here for you. So 275, that's a good one, you like that. 276 and 281. Okay, so these might be a little time consuming or you know, challenging, whatever the heck you want to call them. 1-8, that's 11-8. Okay, so give yourself some time on these, okay? And I gave you the ones previously too, so you'll spend a little time on these, I think. Okay. Are we okay on that? Good to go. Hope everybody has a good weekend.